Okay, so today we're going to be starting Module 3, which is going to be velocity analysis. This is going to be the application of the vector work that we've been doing in the previous module. Okay, so now we're going to apply what we learned there. We're also going to be applying things that we've done in even the previous Module 1, when we were doing our kinematic diagrams and such. So the learning plan for Module 3 is here. You're going to notice that I have it broken out into, if you would, 2 PowerPoint presentations. That's kind of how I'm going to lecture. We'll kind of see how that shakes out today. I don't want to rush through this. We have plenty of time allotted for Module 3. We're going to be exploring Chapter 6, though. So Module 3, I know it's our third module, but we are going to be skipping over to Chapter 6 in our book. So a Part 1, Part 2. So we'll be starting Part 1 today. You'll also notice that there is a handout right here. This is a PDF. I have them printed out in the room if you're in person. We are going to be using that as our practice problems. So there are blanks to fill in and such. It's going to be part of what we hand in for our practice problems. But if you're virtual, make sure that you print off that handout, because then you can fill it in as we do our lecture. Okay. And then you're going to have 2 things to hand in, just like we normally did, the practice problems and assignment 3. I'm not going to worry about assignment 3 right now, but let's take a peek at the practice problems, just so you're aware as we're doing things. Things that you're going to be handing in for practice problems are going to be the 3 items that we see here. Number 1, example 6.1. We're going to be doing calculations only. That's going to be kind of getting us started here in Module 3 or in Chapter 6. And then here is that handout. Again, very same handout as is the link in the learning plan. So whether you get it here or there, it's going to be available to you in the PDF. And then lastly, we have an extra example here, 6.6, that we're going to be using too. And this one's going to be as part of the second lecture that we have to do. Okay. And then also it's going to be the questions, answering those similar to what we did in the past practice problems. So that's why I want to be sure that you understand that the handout that we have is going to be part of what you're going to be handing in. Okay. So as we're going through lecture, you're going to get all the information on filling that in. And I think it's going to be a nice, if you would, companion to our lecture. So with that, what we are going to do is I'm going to go back into Module 3 learning plan, and I am going to pull up the PowerPoint presentation that we have here. And this is going to be our first one. Hopefully it comes up here. Let me move this up here. I'm going to close this for a second. We'll try it one more time. Otherwise, if I have to download it, I will. But sometimes it's just kind of nice to pull it up here. I think it's going. Okay. It should be good now. All right. So Chapter 6 in your textbook is where we're going to be looking for velocity analysis. And again, this is the first part of the lecture. So our objectives here are to look at, in this chapter, linear, rotational, and relative velocities. So many of you, through your experience in, for instance, physics, have had linear and rotational kinematics, if you would. And it's probably been noted that way in your physics classes. But you're looking at, like, for instance, a single link and how, when it moves or rotates around a fixed point, how are, rotational or angular velocities and straight line velocities related? So I know that you've hit that along the way. So we're going to be reviewing that in the beginning here with linear and rotational kinematics. But we are going to be adding relative, okay? Relative velocities and relative kinematics is when we have our linkages, for instance, our classic 4-bar mechanism, where we move one element, normally the crank, okay? And we want to figure out what's happening on the other stuff, okay? It's not as direct, if you would, as just figuring out, how fast it's rotating. We've got to work through those links that are connected to one another to kind of get from input to output motion-wise, okay? We're going to be doing some conversions here. So we're going to be seeing how we convert between linear and angular velocities, or how they're related. We're going to apply the relative velocity method to graphically solve for velocities of a point on a link, knowing some velocity of another. So we are going to be using AutoCAD 2D layouts to get accurate results for these graphical methods. Yes, you could, and I'm not going to have you guys do that. You could use a protractor, pencil, compass to get this very same thing. But as you can imagine, you're not going to get it to 14 place accuracy like we do in AutoCAD. So we will be using AutoCAD to get our graphical methods so that we can get our answers very accurately. And then we're also going to be using the relative velocity method to determine the velocity of what we call a point on a floating link. So that'll be addressed towards the end. So in the beginning here, in our first section of chapter 6.1, it talks about, in velocity analysis, here are the questions or the things that we're going to be doing in this chapter. First of all, we want to answer the question, how fast are certain points on a link traveling? Okay, it might be on the crank, the one that's going to be our output, but most often we're interested in what's happening down the line as we rotate this around or we control the input motion. What's happening on the output? So the determination of velocity in a linkage is the purpose of this chapter, and we're going to be using the relative velocity method. So we're starting in chapter 6 here with velocity. This is the motion part of kinematics. In the beginning, when we defined kinematics, we said it's going to be the first step in our design process. It's part layout. Okay, so we've been looking at, okay, what is the space that our mechanisms are going to be taking up based on the function that they have. So in our last module, 2 modules ago, in module 1, you moved different mechanisms around to see what the output would be. So we determined strokes, or we determined throws, or we determined what were the limiting positions, okay, of those mechanisms. Now what we're going to be doing, that was position analysis. Now what we're going to be doing is we're going to be looking at, okay, the motion. Then that's where the velocity comes into place. How fast are these going to be going as we move them around? So the first thing we're going to be looking at, which again, like I said, in your previous coursework like physics, you would have learned and applied linear velocity. So linear velocity, the variable v, is going to be straight line displacement of a point. And we want to know, like, how much time did it take us to displace? So what is the displacement per unit of time? So the equation for velocity is going to be distance divided by time. Now, in this book, they use the variable r. Sometimes you see it as s, sometimes you see it as d, but whatever it is, displacement is going to be that distance that was covered, okay, that we're interested in. And then divided by t, which is kind of universal for time. Like, how much time did it take for us to cover that distance? So we get it into a rate. Okay, so most often we look at it as, we look at our speedometer and we say we're going 55 miles per hour. Okay, so miles per hour is I'm going to cover 55 miles in a time of 1 hour divided by. So that's why we say per hour, miles per hour. Now, velocity is a vector, which you've already probably have encountered along the way as well in previous coursework. But to fully define it, we need both magnitude and direction. So we can calculate it using the equation that we see above here. How much distance did we cover and how much time did it take us? So we can calculate that value. That's the magnitude of the velocity. But that just gives us a portion of it. To become a vector, we have to know what direction it's going in. So now we're looking at, for instance, using the speed in our car. If we're looking at our speedometer and we're identifying, I'm going 70 miles per hour, that's just going to be a scalar quantity. That's just going to be speed. And you've heard of speed before. It's a scalar quantity. But once I say I'm going 70 miles per hour north, I've added a direction to it. Now I am a vector. Okay, so 2 quantities to fully define a vector. 2 quantities to fully define a vector, and velocity is a vector quantity. Now, the first type of velocity we're going to look at is going to be linear, rectilinear, or linear velocity or rectilinear motion. So that just means that we're going to be going along in a straight line. We aren't going to be rotating around a fixed center. We are just going to be going in a straight line. And to calculate velocity, just like we did in that previous slide, The equation is going to be how much time did, or how much distance did we cover and how much time did it take us? So V is going to be equal to distance divided by time. In this case, again, they're using the variable capital R here. Again, I don't know exactly why. This is unique to this textbook. Normally, I'll see it as D, lowercase d, or as even S is another popular one. So in this case, they use capital R in this book, and then divided by the amount of time. Okay. Now, when we look at units of velocity, they're gonna come from the actual equation. So you'll notice that in this equation, because we take distance divided by time, distance is on top, it's in the numerator, and time is in the denominator, I say on the bottom. So that's going to also coincide with the units that we see. So when we see units for velocity, they're going to be feet per second, inches per minute, inches per second, miles per hour, kilometers per hour, distance divided by time. That per is basically your division symbol, if you would, right? In the equation. So any questions right now on units or the equation for just linear velocity? Again, I know that it's going to be review for you guys. I should pull out the chat box because I want to be sure that if you do have questions virtually as well, I want you to have the opportunity to ask. Okay, so now, oopsie. Let me go back over here. I want to look at example 6.1. So this is the first example that we're going to be handing in as part of our practice problems. Now, this example is found on page 124 in your book. Okay. And what we're going to do is you are just going to write down work only, calculations only. So I'm going to kind of walk through this process with you and what I'm going to be required, but you will be handing in this particular problem. So just grab out an extra sheet of paper that you then can scan or add to the notes that you are going to be handing in for the practice problems. So I'm going to go underneath our camera here. I already have my book open to page 124. Okay, and this is example 6.1. Okay. All right. Now, for this example, because the illustration is there and it's very, and we're not going to need the illustration to do any calculations, all we're going to be writing here is going to be the work, the calculations themselves. You don't need to draw a diagram for this, okay? So we're just going to label this example 6.1, okay? And we'll read the example first. So it says, crates on a conveyor, shown right here, move toward the left at a constant rate. Okay, so not speeding up, not slowing down. We call it constant velocity. All right. Now you're going to notice that we have that velocity V of the crate. Its motion is identified by the vector. So indeed, it is going to the left because we see the arrowhead of that vector going to the left. It says that it takes 40 seconds to traverse the 25-foot conveyor. So that's how long that conveyor is. All right. They want us to determine the linear velocity of the crate. Okay. So to calculate the linear velocity, we know that our equation is going to be V is equal to, now whether you use R or T here or S, I really don't care. I usually default to lowercase d because that's like traditionally what I've always been used to. You probably are too. D divided by T. Okay. I know this is very simple, but I also want to give you the formatting for what I expect for you to hand in for not only the practice problems, but for assignments that are going to be related to this as well. Notice that I identified my equation in variable form. And just as a review, for those of you who have me, you know that I insist on this, but those who might be new, notice that when I show an equation that has a division in it, we don't use a slash, okay? We use numerator, denominator, numerator on the top, denominator on the bottom. Do not, and I will not accept velocity is equal to D divided by T. Will not accept that. We do this strategically because we're going to be adding our units in all phases of the problem, and we'll have to do cancellations. If you write this out and you say, well, I see them, I don't care. This is how you're going to be writing it out if you want credit for it. You will lose points on the assignment if you show divisions with a slash. Okay, I'm telling you that right now. So much of the work that we do, not only in this class, but I know you've had me for statics, we did it there, but you're going to have other courses that are coming up as well, like machine design elements. You've got to see that your units come out correctly in the end. And so you're going to have to show your units in all phases of the problem canceled out, and things that aren't canceled out, then show you your final units. If you have the final units correct, you can be quite certain that you set up the problem correctly. So that's a huge benefit of showing your work and also showing division problems in this manner. Okay. Numerator, denominator, top, bottom, no slashes. All right. So now that I have my equation in variable form, and I'm gonna get rid of this. Okay. Now what I'm gonna do is I'm gonna add my numbers. So the first thing I'm looking for when you show me your work is, do you have the equation in variable form? All right, so we have it. So then I'm going to add my numbers in here. So distance, as I look at this crate, the distance that it's covering, it tells us it's covering 25 feet. So I'm going to put 25 feet. So the number with the units directly in back of it. If you don't put units in and you just put numbers, you don't get points. Points will be deducted, or you'll just get a 0. That's like nails on the chalkboard for me. Okay. Have to have your units in all phases of the problem. We're not going to have units magically appear at the end. I'll tell you a really quick story. You might be rolling your eyes. Don't do it in front of me because it hurts my feelings. Okay. You might be like, why is she having us do that? No other instructors have us do that. It is super important. I used to teach physics. Okay. So my mechanical design students, they always were like, it's just what she does. We're just going to follow the rules, whatever. But then when I taught physics, I was teaching it for a couple different program areas. So it was not only mechanical design, but it was electronics and nuclear. And I think there was one other one, wind or something like that. But they were all, they had the requirements. So when I started talking to them about exactly this, okay, problem very similar to these types of problems, I would say you have to show all your units. And they would visibly like kind of get mad at me. Like, I'm like, oh, okay. But I explained to them exactly what I explained to you. As you go along and you even apply this in other places, when you don't get the correct units, now you have a reason to go back and check to see if you have it set up correctly. Okay, that is the main part. So as we went through the class, I kept insisting on it and they got used to me. They started applying it in other places and they were like, other things make more sense now when we look at it. Don't just magically make your units appear at the end, okay? Because you never really have full confidence in it then, all right? So this is a layer of assurance that you set it up correctly. And as we know, 98% of a problem is the setup, right? If you don't have it set up correctly, if you divide instead of multiply and all that kind of stuff, then all of a sudden, you know, it's hard to detect where that is. So that's my little rant today on making sure you put your units in, okay? So do it. So then we're going to go divided by the amount of time that it takes me to move 25 feet. And it told us that it was 40 seconds, right? So we're going to put in 40 seconds underneath here. Now, as we look here, we would take this opportunity before we would solve to cancel or combine any units that were there. And in this case, there are no cancellations because we have unique units top and bottom. But it now reveals to us our units for this would be feet per second. Okay, feet per second. And so then we just have to kind of know, are those appropriate units for velocity? I say yes, yeah, right? We know that velocity is going to be in distance divided by time. So we see that the right units are here. And then we also can then say and have confidence that we have this set up correctly. I know this is easy, but it's a great way that you can, you know, get something that you're expecting and then again, kind of see the process play out. So my number for velocity then is going to be 25 divided by 40. What's my number? 0.6 what? 65? 625. Yep, 3. I like the 3 significant digits. And then I'm going to be adding to this feet per second. Okay, now the other thing when you show me a final answer, don't just show me the number, okay, and put a thing around it. I want you to answer the question. And the question was, determine the linear velocity. So the variable for linear velocity is v. you need to say V is equal to, and now you're going to put a box around your final answer. That tells me definitively I've ended this question, and I want, this is what I'm presenting to you, Kelly. Okay, and then I'm seeing the work above. So if I look here first, and this is what I do, I'll look to the final answer first. I'll indeed see that it's the correct value, as well as formatted with the units always, and the variable identified. And then I look above. Did you show all your work? Did we see these units, kind of boil to the top, if you would, here, and make sure that you had it set up correctly, okay, and that the numbers were in the right place. Any questions on that? All right, so put this aside, put this somewhere. This is the, this will be then what you hand in for example 6.1. All right, let's get back to our PowerPoint presentation. And the very next slide here, there aren't many slides in this one, we're going to now switch gears and go over to our handout. Something that I feel this book is light on is relating the concepts of linear velocity and angular velocity. And so what I do is I take some extra time to do that in the handout that we have. So if you would, we're going to be spending pretty much the rest of the time in our handout. I'm going to go underneath here. Here is that handout, velocity handout in Module 3. It's a PDF. Again, make sure that you print it off and follow along here. So the first page here is kind of laying the groundwork for us for the relationships and the equations that we're going to be using, okay? So let's kind of start at the top here. And then as we move through the handout, there'll be things that we're going to be filling in and calculating. So first of all, linear velocity, we had just looked at that. Linear velocity is going to be calculated using V as its variable, distance divided by time, okay? In this case, on my handout, I have S. Like I said, S and D are the most popular ones. This book does R, but it's a distance, okay? So in the case that we just looked at, we had that conveyor belt. We wanted to find out how fast is that moving per unit of time. We can look at our car. If it's moving down the road, we can determine how fast it's going on average or at that moment. Or somebody that's walking a certain distance, okay? How much ground did they cover and how much time did it take them? As we look down below, we move into a different type of motion, and this is going to be rotational motion. And in this case, we have a single link, rigid link, that is going to be rotating about a fixed center. So as you can see here, I have a kinematic diagram, if you would. Number one here is the frame. We're using that frame symbol so that we can see that point A, which is connected to link number 2, right there. That point A is going to be the point at which it is affixed, right? We're using that frame symbol, and we know that that's not moving. So that means that this link is rotating and only has the ability to rotate about that fixed center. Now, we say that the entire link has angular velocity. Angular velocity, sometimes referred to as rotational velocity, but angular velocity is going to refer to the entire link rotating around the fixed center A. Now, since the link that we're interested in is link number 2, we would call this W sub 2. This is the W. W is the symbol, universal symbol for angular velocity. So as you can see over here on my diagram, I have the direction of the angular velocity identified here as W2, or it's really Greek letter lowercase omega sub 2. Okay. Now, notice that my angular velocity has direction. So the direction that that arrow is pointing, in this case, clockwise, gives me the direction of the rotation for that link. So that link is going around in a circle, if you would. And at this point in time, we're just looking at it at this instant, like it's kind of frozen in time. We have it in this position. All right, so any questions about that? W2 is angular velocity. And again, we're using our standard callouts like we've been using for kinematic diagrams. Number 1 is the frame symbol for something that's not moving. And then I didn't draw a line. I just kind of drew a link so you could see it was, had some thickness, if you would. But that's link number 2. Now, you'll notice that we have points X, Y, and Z along the length of link number 2. X is here, Y is here, and Z is here. Okay, those are points on the link. Now, Every one of those points is rotating on that link, but they also have a linear velocity component, and you see it drawn for each one of those points, okay? So the linear velocity, Vx, is right here. Linear velocity, Vy, is right here for point Y, and then Vz for point Z. So it's the velocity sub whatever point that it's around, so X, Y, and Z. Now, you're going to notice something about the direction of the velocities. Number one, the direction of the velocities is going to be in the direction of the angular velocity. So since the angular velocity is rotating this link clockwise, if I was to go around and around and around and around, and we would suddenly stop right in this position with this link, and let's say these points Z, Y, and X are not affixed and they're free to continue to travel, this link would stop and they wouldn't continue to travel in a circle. They would continue in a straight line, right? We know that. Again, you guys have, I'm certain, seen that in physics along the way. Okay. If anybody has ridden, and I know all of you have probably, on a merry-go-round at the playground, right? I'm on a merry-go-round. The fixed center is the center. And this would represent the radius out to the edge of the merry-go-round, right? So the merry-go-round goes around and around and around, and we've all, gone really fast, maybe stood on the edge when you're big kids, and then you kind of have fun, maybe if you would, falling off or maybe jumping off, but you don't continue to go in a circle. You would go in a straight line, actually tangent to that path, right? So we kind of can experience that. Now, the question, though, is, or what you might be interested in, or another relationship that we see, is that the velocities are also perpendicular back to their radius of rotation. So if we look where point X is and we take a line and we go directly to the center of rotation, this line right here, our velocities are perpendicular to it. So notice that I use that 90-degree symbol for the direction. So not only do they go in the direction of rotation, but they're perpendicular to that radius back to the center of rotation. Okay, right? That's important for construction when we start looking at graphically drawing these in AutoCAD. Okay, velocities are always perpendicular to something. Straight line velocities are always perpendicular to something. You just got to find what you're perpendicular to. And in this case, it's the radius back to the center of rotation. Okay, so those are directions for us. Now, magnitudes. Notice that the length of the velocity at X is shorter than the velocity at Y, which is also shorter than the velocity at Z. And this is because there is a relationship of the magnitude of the velocity is going to be equal to the rotational speed, W, the angular velocity, times its distance from the center of rotation. So the distance from the center of rotation to point X would be, if you would, R, lowercase r, I'm going to try to scooch it in here, Rx, this distance right here, okay? The distance between the center of rotation, it would be the radius to point X, a distance. Then the radius of point to point Y would be to here. So this would be the Ry. And then the radius to point Z would be Rz out to here. So as that radius gets longer, our velocity is going to increase. Now, let's think back to our merry-go-round example. Does that make sense? Okay, years ago, when I had my little toddlers, we would go to the playground and they would play, and obviously they would, want to go on the merry-go-round. Usually the big kids were going really fast, right? They were spinning it around really fast. So me, as a concerned mom, and I didn't want my little toddler to get hurt, I would set them towards the center of rotation. Okay, sit there. Okay, you can be with the big kids. That's fine. You can go on here, but I want you in here. I wasn't going to set my 2-year-old out on the end. Okay, unless I was rotating the merry-go-round. Okay. Why did I do that? It's more fun on the end. Any ideas? Why did I set my toddler towards the center of rotation rather than out at the edge of that merry-go-round that was maybe spinning a little faster with the big kids controlling it? Well, oh, go ahead, Ben. Yes. So in this case, if I'm here, right, my velocity is much less. So if my toddler would fall over on the merry-go-round, they really wouldn't like slide very far, right? But if they are on the end, now they're going a lot faster. It's harder to hang on, like as we know, and they're going to be going a lot faster, which then they could get hurt, right? So the reality is that. So velocity increases the further we get away from that center of rotation. Okay, so in this equation, V is going to be your straight line velocity. We call that component of the motion. W is going to be the angular velocity. Every point along this length, any point along that length, that entire length and every point on it has the same angular velocity. Because out here, I'm still going 20 revolutions per minute. Okay. I'm also going 20 revolutions per minute here and here and here and here and here. It's all the same. So the W remains the same as we rotate for anything along that length. The difference is the radius, or the lowercase r. That radius is going to change depending on where my location is in relationship to that center of rotation. Okay. So these couple points here, everything on that link rotates at a angular velocity, in this case, W2. We could have a W3, we could have a W4, okay? But in this case, this is just called link number 2. X, Y, and Z have linear velocities associated with them, and their direction for those linear velocities are always going to be number 1 in pointing in the direction of rotation, and number 2 perpendicular to that radius back to the center of rotation, okay? And then magnitude-wise, we can calculate that velocity anywhere along that link. Okay, questions? How many have seen like this stuff before? Okay, maybe, okay, good. And we will continue to apply this, all right? So let's turn the page, and there's some stuff to fill in back over here. Okay, so let's look at units. As you know, it's a big deal to me to fill in units for things. And again, it's important to know and understand what are the units I'm expecting, so that in a final answer for a problem, you can look at what is like left, hasn't been canceled out, to confirm that you indeed have the appropriate units to make sure that your setup is good. So first of all, straight line velocity. What are units that we would be expecting for straight line velocity V? You can look on the previous page if you want to. What are we thinking? There's multiple options. There's not one right answer. And those who are virtual, you guys can put it in the chat if you want. I'll watch. Shout it out. Or write it in.
Over time.
It's going to be distance over time, but I want units. Units. What was that? Units, yeah. What would be a set of units for velocity? What would be an appropriate set of units? You're right. It's distance over time is the equation. So what are the units associated with that? Meters per second. Yes. Meters per second would work. What else would work? Feet per second. Yes. We could add feet per second. What else could we add? Miles per hour. What else? I won't put them all down at this point. More in the classroom. Anybody? All of my answers have come from the virtual folks. So we have meters per second, feet per second, miles per hour. What else? Is that it? Inches per minute. Absolutely. Inches per second, meters per minute, right? All of those things. So anything that would be distance divided by time. Distance divided by time. So put at least one of them in here. All right. Whenever I show units, identify units in a in a handout or writing it out, I don't know if you've had me before, you've noticed that I use brackets for units and then parentheses for regular variables and equations. So the next one, if I want to identify units that would be for instance, a radius, which is a distance, what would be appropriate units for a radius / distance?
Meters.
Meters would be one. What's another one? We're going to be shy. We all know each other at this point. We're going to be shy. It's going to take so long to get through this. Wow. Ben. Feet. Yes, feet is going to be another one. What else? Centimeters. Perfect. What else?
Parsec.
A what?
A parsec.
I don't know what a parsec is. Inches. Is it a distance of some sort?
Huh?
Is it a distance? Millimeters. Yes. Yes, yes, yes. So anything that is a distance measure. If I'm going to take a ruler and I need to measure something, those values are going to be considered a radius or a distance value. My shoe's coming up. Angular velocity. This is our W. Tell me what units would I be expecting for angular velocity? We didn't talk much about that, but you might know. Any idea? Angular velocity, something that's rotating. What would be appropriate angular velocity? RPMs, or top down, we would do revolutions per minute. Okay, revolutions per minute. We're also going to find out that radians per second is the other one too. Okay, and actually we'll talk about that in a little bit. Yes, 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 yes. So you can put here radians per second. Okay, those are also appropriate. Now let's talk about radians per second and RPMs. So RPMs, revolutions per minute, and radians per second are both valid units that we use for angular velocity. Now, the difference between them, first of all, revolutions per minute. We can relate to revolutions per minute. If I say my merry-go-round is going around 20 revolutions per minute, that means it's going to go around 20 times within 60 seconds, right? If I specify or I identify a motor speed at 1700 RPMs, that means in 1 minute, 60 seconds, that's going to rotate. It's going to have a revolution. I'm going to get I'm going to get 1700 revolutions in every minute. That's going around pretty fast. Okay. Now we can usually relate to RPMs. It kind of makes sense to us. We can kind of, conceptualize that. But when we're calculating and using W in our rearranged form of our relationship between V is equal to WR, all that's doing is taking the W and it's getting rid of the R on the other side, and it's just solving for W in that equation. When we are using that I always say in and out of that equation, we will always get radians per second, and let's see why. So if we look at the top here, we're going to put the units in for velocity. So above the division sign here, or in the numerator spot, for velocity, we know that that would be distance over time. I'm going to use inches per second. So I'm going to say inches per second on top. Top, bottom, not a slash. Divided by radius or distance. And having consistent units, we would put inches in the bottom here. Now, when we do that, this is cancellation. So we would cancel out the inches top and bottom, right? So now we basically have nothing per second. But what happens? We are rotating. This is angular velocity. Radians are going to magically disappear, or magically appear. I'm sorry. They're going to appear. So we're actually, when we're rotating, we're in radians per second. So when we get to that point where we're like, oh my gosh, the inches canceled out, it's nothing per second. No, no, no. It's radians per second. You guys remember that from your physics? Okay. Now, when we use it in this equation, like I said earlier, if we divide by this, we're going to end up with radians. But if we're given angular velocity in a problem, because a lot of times that's what we know the most about. We have maybe a motor connected to a link. It's going to rotate that link at, I'm going to just use 1750 RPMs. That's going to be our known, but we can't insert it in our equation to solve for anything else as RPMs. We're going to have to then convert the RPMs to radians per second to use it in this equation. Does that make sense to everybody? So directly below here, we're going to practice exactly that. We're going to practice going from revolutions per minute, getting it into radians per second, and we're going to go from radians per second and putting it into revolutions per minute. Now, this is the deal. We are writing this out. You are writing this out always. You are not going to go to one of those calculators online that's going to say multiply revolutions per minute by this number to get radians per second. Not going to happen. You are going to be writing this out each and every time, and I'll be demonstrating that through the problems that we do. So we are going to be using the ratio method. And the reason we use the ratio method, and I introduced it here to you guys, and if you've had me before, you've seen this also, but there's never, ever going to be a question about the units that you get. Remember, units are super important. We only need to know a couple unit conversions and we can get pretty darn far, okay, with this ratio method. So as you notice here, I have my unit or my quantity of 500 revolutions per minute. First of all, I get it in RPMs, but when I'm going to convert, I need to expand this so my revolutions are in the numerator and my per minute is down in the denominator, okay? Then you're going to notice that I use vertical lines here and horizontal lines. Those are just going to identify my unit conversions, okay? So as we look here, we've got revolutions on top and we have minutes on the bottom. I need to get this into radians on the top and seconds on the bottom. So I'm going to start with my revolutions. If my revolutions are in the numerator, that means that directly down here, I'm going to put revolutions in the denominator, and I'm going to put it in 1 revolution in the bottom. Okay. In the top, directly above it, I'm going to tell it, I'm going to put how many radians are in 1 revolution. There are 2 pi radians in 1 revolution. There's the conversion, top bottom, the ratio that I created. And the position of the revolutions and the radians are dependent on the units directly in front of it. So if revolutions are in the top here, they're in the bottom here, because I am going to multiply across the top and divide by the bottom. So I want my revolutions to cancel out, so I end up with radians. That's my desired numerator units. Does that make sense to everybody? This takes out the guesswork of, do I multiply by or do I divide by? Okay, you don't have to worry about it. It's right here. And I will not accept if you get one of those calculators that say, oh, multiply this number from RPMs to radians per second. That is not ratio method. You're showing each one of these out. Okay. Then we're going to do minutes. Okay, so right now, if I multiply across the top, divide by the bottom, my revolutions cancel, and you will cancel the units. And I have radians, if you would, per minute, but I need this in radians per second. Notice that the minutes is in the denominator. So now that means that my minute in my next ratio is going to be on the top here. So 1 minute is going to go on the top. And directly below, I'm going to say is equal to 60 seconds. Minutes are going to cancel. And now you're going to notice the uncanceled units are radians per second. Okay. Which are the units that I want to end up with. So now what I'm ready to do is to determine my value. I'm going to multiply across the top, divide by the bottom. So 500 times 2 times pi divided by 60. What do I get for my value in the front here, my actual magnitude?
1,141.
No, that shouldn't be it. Try again. So you're going to take 500 times 2 times pi, and then you're going to divide by 60.
2.3.
Does anybody else get 52.36? Because everybody should have their calculator out and doing it, not waiting for other people to do it. You're going to get the opportunity to do this when you're doing your homework. And then you're going to be like, how did they get that answer again? I don't remember. Okay. So the answer 52.36. Does everybody get that on their calculator? That's part of, don't just sit back and let other people do it, because number one, lecture is boring then, or demonstration is boring. I don't like using the word lecture because it does sound boring right away. And this is not boring. I mean, this is like riveting and interesting, exciting stuff, but it's going to make it more interactive. That's what I'm trying to say. Okay. Then let's do the one right down below it. So we're going to do it in a different order though. This time we have 10 radians per second, and I want to determine how many revolutions per minute are. So go ahead. I'm going to give you 30 seconds to fill that in. Not a race, but just fill it in first, and then we'll look at it together. So I'm going to give you a little bit of time to fill that in and see if you can get the right answer. How many have done the ratio method before for unit conversions? Excellent. Good, good, good. All right, let's start looking here. So I'm going to start by converting my radians to revolutions. So since radians is on the top here, right? Radians per second, top is going to be, the numerator is going to be radians, denominator is going to be seconds. That means that I want to put my radians opposite. So 2 pi radians is equal to, directly above, 1 revolution. So multiplying across the top, dividing by the bottom, my radians cancel out. Then I want to get this into revolutions per minute. So I've got revolutions per second right now. I've got seconds in the denominator. That means that seconds is going to go up here. I know that there are 60 seconds in 1 minute. Okay, so my seconds are going to cancel. So now you'll notice that the uncanceled units are going to be revolutions on top, minutes on the bottom, which are consistent with RPMs. When you write it as a final answer, you can write this as RPMs. I will tell you that. You don't have to write it revolution per minute, but when you're converting, you have to expand it out top, bottom, okay? So what do I get for a number? I'm going to multiply across the top, divide by the bottom. What do we get for our answer here? How many revolutions per minute is that? Everybody should be doing it. Ben. 95.5. Anybody else get that? That's consistent with what I have too. Awesome. Thank you. Thank you, Peter. Thank you, Tyler. Awesome. Okay. Converting units. What was that? Oop, try again. 10 times 60. Yep, there you go. Oh, you did it by the 1. Yep. Don't forget the start. 10 times 60 divided by 2 divided by pi. Awesome. All right. Any questions so far? Okay. Look at that. We get to do our first example. This is so good. So example number 1 on the following page here. Again, we're going to be filling this in. You're going to be handing this in as a part of your practice problems. So example number 1 says, we want to determine the straight line velocity at point B as line or link 2 rotates 100 RPMs counterclockwise. So right now we have, if you would, our kinematic diagram. We have link number 1, which is the frame, does not move, is connected to link number 2 here. And it says that it is rotating at 100 RPMs counterclockwise. So first of all, we want to add the designation for our rotation of this link, okay? So the rotation of the link is going to be going counterclockwise. So it's going to be rotating about that center. So we usually show it like this as an arc. And then we're going to put the arrow in the direction of rotation. So counterclockwise would be, if you would, going to the left. And then we're going to label this W2. That means that it's the angular velocity of link number 2. Okay, these are going to be labels that we're going to be adding using our CAD later on as well. Okay. All right, so that was this. So our, if you would, W2 is equal to 100 RPMs, okay? And that's a given for us. We want to determine the straight line velocity. Straight line velocity is going to be V, okay? So now we want to draw that straight line velocity of B. B is the end point of this link. Now, a lot of times we're going to be dealing with endpoints, and the endpoints are the extremes, if you would. As we saw earlier on the first page, okay, if we go back here, we saw that as that radius of rotation increases, and the most it's going to get is going to be the edge of the part, the velocity is going to also increase. So that's going to be its maximum velocity. We're usually designing, if you would, worst case scenarios. So as bad as it's going to get or as fast as it's going to get is going to be out at that endpoint. All right. You could calculate for ones in between if you're interested in that. And there are reasons, I'm sure design wise you would be, but most often we're going to see the end be what we're interested in. And that's exactly where B is. So we want to draw the velocity vector showing the relationship of that straight line velocity of point B as it rotates on this link. So to do that, we want to keep in mind its direction. So number one, we know that our velocity has to go in the direction of rotation, right? So in this case, this is rotating counterclockwise. So we would expect that this is going to be going like that way, right? We also want to draw it. The other thing about direction is we want to show it perpendicular to its radius back to the center of rotation. So this line is depicting perfectly perpendicular, perfect straight line here, back to the center of rotation, which is going to be A. Our velocity of, oopsie, that doesn't look very perpendicular. Our velocity at B is going to be perpendicular to that link and pointing up and to the left. And we would label this then VB. Okay, and again, this is going to be perpendicular there. So just drawing or sketching it in place. So you want to add those labels that we just added. Now, this is the quantity that we don't know. So this is going to be something we're going to calculate, and we know W2 to be 100 RPMs. All right. So to determine that, the relationship between straight line and angular velocity comes directly from that very first equation. This is normally the standard form. V is equal to WR. So go back over here. We're going to say VB because that's the variable. Don't just put V because we're calculating or we're determining the velocity at point B. So it has to be V sub B. It's going to be equal to our angular velocity of the link that this is on. The link that this is on is link number 2. Okay, so make sure that you designate it that way. So you're showing it as the label up here, and you're showing those very same labels in the variable form of the equation. And then our R times R, and that's going to be R sub B. So it's going to be the distance from the center of rotation out to point B. And the 10 inches here, that's going to be equal to our RB. Okay. So now we can put our values in here. Okay. So I'm going to say equal to 100 revolutions per minute times 10 inches. Okay. So what do we get for VB? A 1,000, right? And what are our units? What are we expecting for units in this case? If inches is our length, velocity should be in what? Inches per second, right? Inches per second. So I'm going to magically just enter those in at the end, and I'm going to put a box around my final answer. Am I good? Absolutely not. Why am I not good? Number one, I don't see inches anywhere. I don't see seconds anywhere. I don't see any cancellation of anything. So how did my inches magically appear? Inches per second magically appear? Because That's the units I'm supposed to be getting, right? You want to prove that you get them. So this is not correct, not correct. Erase that. Don't enter that. That is not practice problem material. That is called a learning moment. What do I need to do? How can I get inches per second? Convert what? Sure, minutes to seconds, but then I'm going to have revolution inches per second. Remember, in and out of this equation, my W has to be in what? Radians per second. I cannot use my RPMs in this equation. Can't use it, okay? We have to convert it before we put it in, all right? So we're gonna have to do a little bit of work before we put this in here. So we need to convert, I'm gonna put it right here, my W2, my 100 RPMs into radians per second, okay? So we're gonna do 100 revolutions per minute, okay? And now I use the vertical lines. I encourage you to do that as well. That way you see over on the side here, it's noticeably a unit conversion as opposed to being an equation with variables, okay? So I'm gonna do my 100 revolutions per minute, top, bottom. Remember, not a slash and not RPMs. We have to expand it out. So I know that one revolution, I'm gonna put it on the bottom because it's in the numerator on the top here. It has to go in the bottom here, is equal to 2 pi radians, right? That's my first one. So that gets rid of my revolutions. Then I need to get my minutes into seconds. So I know that 1 minute, put it on the top because minutes is on the bottom here. I need it to cancel. It's going to be equal to 60 seconds. Minutes cancel here. So my W2, I'm going to multiply across the top. I'm going to divide by the bottom. Tell me what you get for W2. I don't have it in front of me, actually. We'll have to ask a couple people to confirm. So 100 times 2 times pi divided by 60. What do we get for W2?
1.47.
And that would be radians per second. Did anybody else? Oh, Tyler got the very same thing. Cool. Cool. Anybody else? Everybody else got it? Cool. Yep, just confirm. So now this is the W2 that we're going to put into here. Okay. So we're going to say 10.47 radians per second. Top, bottom. Don't do it radians slash seconds, remember. Okay. Times our radius is the 10 inches. Okay. So now when we multiply these two out, VB is going to be equal to, looks like 104.7. And now let's talk units. Okay. Thank you, Kangmen. Good. And Ben, excellent. You guys got the same answers. Perfect. So now we've got 104.7, 10.47 times 10. That's my magnitude, right? My number. Now units, radians per second times inches. I'm still looking for inches per second, right? What happens to the radians? Do I put radian inches per second? No. Radians, if you remember, are dimensionless or unitless, right? I say, they're like Lucky Charms. They magically disappear, right? So if radians are multiplied by something, radians drop out. So radians times inches on top is inches per second. There are your final units. So whenever you multiply by radians, they magically disappear. When you end up with nothing per second, they magically appear, okay? Radians will pop in, okay? So questions on that first example. All right, cool. Now we're going to go on to example number 2. This is working it a little bit differently. In this one, we have a similar setup. We've got link number 2. This time it's 15 inches to point B. And we're showing that it has a linear velocity. Now, it doesn't say VB is equal to 250 inches per second, but there are clues. Why do I know that VB is 250 inches per second? Why am I pretty certain that the 250 inches per second is the velocity at B? How do I know that? What are some clues or hints that I have?
Velocity.
Yeah, it has the units of velocity because we know the units of velocity. That's one thing. What's another thing? The vector, right? The vector quantity. Velocity is a vector quantity. So this is a line with an arrowhead on it, as Noble had said. That's a vector. So angular velocities are not depicted as vectors. They're depicted as like rotational things, right? That's not a vector. This is a vector. A straight line with an arrow is a vector. So velocities are depicted by vectors, which we see here as it's called out from from point B, and its units are inches per second. Perfect. So I know. So I'm going to label that my straight line velocity at point B. Okay. It wants us to know what the angular velocity of link number 2 is. So angular velocity is that W business, right? So I've got to label W2 here. So I know that W2, or the angular velocity, is going to be rotating about that fixed center. Is this going clockwise or counterclockwise? Am I going to show my arrow here or here? Ben.
Clockwise.
Yeah, it's going to go clockwise. You are correct. And why did you choose clockwise? Ben on virtually also said clockwise. So this is going to be my W2. That is correct. What was your clue on that? Yes, and Ben did it as said to the very look. I got Ben in class and I got Ben virtually. So yes, it's going in the same direction as that straight line velocity. So if you think about it, if I put my finger at A and I pull in the direction of the straight line velocity, that's also giving me the direction of my angular velocity. You guys remember doing that? Putting your finger on things, moments. Maybe you didn't have it for statics. You didn't get to do that. All right, so perfect. So we've got our W2 labeled, and that's what it's asking for. So we want to know, what is W2? Okay, and we have straight line velocity, and there's another variable here that we know, and that is going to be our radius to B, which is going to be our 15 inches, right? That's our distance from the center of rotation to the point that we're interested in, or we know information about. All right. So we want to find W2, right? We want to find W2. What is its value? We can put the question mark there as well. So equation wise, what equation am I going to use to solve for W2? We've seen 2 forms of the same problem. We've seen on the first page, this form of the equation, V is equal to WR. And we've also seen it rearranged. It's really the same equation, just rearranged. W is equal to VR, V over R, sorry. So since we're wanting to find W, right, this is going to be the form that we're going to use here. So we will start by saying, okay, W2, because that's the W we're solving for. Don't just start with W here. If it's on link number 2 and you've got it identified up here as number 2, then you need to be showing it in your equations with those same variable callouts. Those little details are important, okay? Especially when we start looking at multiple links. We're looking at one link right now. We're kind of getting warmed up to this. We're looking at one link, but when we start having multiple links in a mechanism, when we start looking at relative velocities, it's going to be really important because we're going to have the opportunity to calculate multiple W's. So make sure you're putting your sub 2 here so that we know it's the angular velocity of link number 2. This is going to be the velocity at, now what's the known velocity? Point B here, divided by the radius to point B. So notice you have each one of those with the correct point or link call out. All right, so now we're going to put in our values. So I'm going to put those directly next to it. So this is going to be 250 inches per second on the top. Do not put inch/second. Break that habit. Resist that urge. Okay. Do you guys do top bottom a lot? You probably see it a lot. It's so much easier, especially when you're doing these cancellations. Physics, I know, is a great application of that. And then our radius on the bottom here is going to be 15 inches. So as we look, first of all, before we even worry about our number, let's cancel out any units, right? So we have inches on top, canceling out inches on bottom. And this is where I always look at my units before I even calculate anything, because if my units don't come out the way they're supposed to, then there's no reason trying to figure out if my number, or try to figure my number, because it's probably not set up correctly. So you'll notice here that I have in my numerator nothing, because inches canceled out, per second. Or is that really what I have? What do I have here as the final units for my W2? Need to look back. Remember, when they both canceled out top to bottom, radians magically appeared. It's radians per second. So as I said earlier, in and out of this equation, it's always going to be radians per second for our W. So whether we're inserting the W like we did up here, we had to convert it to radians per second before we used it. Or if we're calculating for it, we're going to get our units to be in radians per second. And it looks like Peter already calculated our value. It's 16.67. I'm going to peek. I'm not, yep, that looks like it's correct. Did everybody else get 16.67? Oh, Ben did. Perfect. Radians per second. Excellent. And this is W2. Now, they told us they wanted us to solve for an angular velocity. Hear me here. When you are specifying an angular velocity as a final answer, you're calculating for an angular velocity. You do not leave it in the form of radians per second. Okay. For instance, if I was attaching a motor to this and I would go to the motor store and I would ask, could I have a motor that goes 16.67 radians per second? They'd be like, I don't know what you're talking about. Or if you go online and you want to order a motor, will you ever see 16.67 radians per second for the units? The answer is no. No. You're going to have to specify its revolutions per minute. Those are the standard units for things that rotate. So if you are asked to determine an angular velocity for me, don't leave it in radians per second. You'll get the answer out of this equation in radians per second, but now we need to convert it to RPMs. Okay. So you're simply going to add the conversion here. So I have radians per second. So my radians, 2 pi radians, are going to go on the bottom in 1 revolution. Okay. Radians cancel. I'm now in revolutions per second. I need to get to revolutions per minute. So 60 seconds on top, right? Opposite of what it is in 1 minute. Seconds cancel. My uncanceled out units are revolutions over minutes, or revolutions per minute. So now I'm going to take this number, I'm going to multiply across the top, divide by the bottom. What is my W2 final answer in RPMs? $159.19. Very close. 159.19. Anybody else get that? Noble is nodding. Peter is saying yes. Okay, make sure you can get that. Put a box around your final answer. W2 is equal to your number with RPMs. Do not leave it at radians per second. Points will come off on an assignment for that. Okay. All right. Questions so far? All right. Peek at the next. What we're going to do is I've been talking for a little bit over an hour, and I always think it's a good idea to get up and stretch a little bit. So we're going to take a break. And when we come back, we will continue on with page number 4 in our handout. So I am going to stop the recording here, move this way. And when we come back, we will resume.